explanation of order here. Nicolletta Noceti from the University of Genova will be speaking to us about biological motion understanding for human-robot interaction.
Thank you. Good morning, everybody. Yes, I'm going to present some preliminary results of this rather young work, let's say. So I'm not going to show you ICAP doing things. This is a joint work between the University of Genova and the RBCS department from the IIT. And it is a work which lies somewhat in the middle of a variety of different fields, from cognitive science, robotics, computer vision and machine learning. I am a person with a computer vision and machine learning background, so I'm going to speak more about machine learning and computer vision and probably less about robotics. Anyway, the goals of this project is to study, let's say, and design also computational models for perceptual primitives, which are the basis of the acquisition of social skills in very young humans. And the perspective is that of using such model with the humanoid robots to mimic the same kind of development and also in perspective use them to improve, to favor the interaction with humans. And of course, such cognitive processes have been deeply studied in the field of cognitive science. And in particular, all these things are related to the so-called theory of mind, which explains how and why we have this ability, which is in part innate, in part learned from a previous experience, of interpreting and understanding the actions and the expressions of other people. As you can imagine, of course, there is a variety of things that may be of interest in the context of robotics and vision. In this project, we deal in particular with the problem of understanding the presence of biological motion in the surrounding scene. Since the very first days of life, we are very good in understanding the presence, in perceiving the presence, of course, of our mother, but also it has been experimented on very young babies, but also on animals, for example, on chicken. That there is a preference, a spontaneous preference towards biological stimuli with respect to non-biological stimuli. So as I mentioned before, the ICAP is the robotic framework we have in mind. From the standpoint of the semantic content of the videos we are considering, we consider both sequences of well-defined gestures, human gestures as lifting actions, transporting objects from one position to another, pointing actions, and so on. But not only biological motion is also me while I am gesticulating in front of the camera, for example. And of course, we also need examples of non-biological motion, so we produce some kind of in-lab videos of a pendulum, for example, or a bouncing ball, or a toy car, and things like this. From the standpoint of video analysis, we consider a rather common and popular pipeline. We start from an image sequence, extract low-level features, and then use them to segment the image in space and time. At this stage, we use optical flow. And then we abstract such low-level measurements in a different space. So we map our representation in a different feature space. So to capture, in some sense, the peculiarities of the biological motion. We will discuss this aspect in a minute. And then the last step is based on machine learning with the aim of distinguishing between the biological examples and non-biological examples. And yes, if I will have time, I would also like to discuss an even more specific application in which we want to infer the weight of an object involved in a manipulation action just by simply observing the action itself from the same kind of data we consider in the other task. Okay, so we start from the optical flow. We compute the magnitude of the optical flow and threshold the map that we obtain, and then from this we can build a sort of silency map that allows us to detect the region of interest, which is the region of the image in which the motion is occurring. From this point, we collapse all the information of a region of interest in a single point, which is the centroid of the region of interest, and all the information of the dynamics are related to this point. So we study the evolution of this point to describe the action. Talking about motion, it can be described in general by two functions. The first one is the function of the shape, the trajectory. The second one is the law of the motion, describing the evolution over time of the action. In principle, these two functions might be independent, but it is not the case for physical events, as in the case of biological motion. It has been experimented that for physical events, there is a rather specific function relating quantities that describe the motion, and in particular the velocity, the tangential velocity, and the radius of curvature. And in the case of biological motion, the function is even more specific. There have been experiments in a rather controlled settings, let's say, and rather specific human actions that were drawing movements, in which they observed that in that specific case, the exponent beta tend to be very close to 1/3. Okay, and then there are some other ingredients, in particular, in the case of that alpha. If alpha is 0, and it is the case when in the trajectory there are no points of interaction, we can rewrite the law with respect to the angular velocity and the curvature. And in this case, the exponent is close to 2/3, and so this is the reason of the law, let's say. So we started to ask ourselves whether it was possible to mimic the same kind of experiments on our data, which has been derived from a rather noisy and more general setting. And so we started to think about a way of, let's say, extracting some kind of computational features to mimic the quantities involved in the law. So the velocity may be derived directly from the optical flow components, and then you can compute as the first derivative of the velocity the acceleration. These are examples of our low-level features. So you have the two components of the velocity, and on the third plot, the trend of the magnitude of the velocity over time. The plot is related to a sequence of lifting actions, as the one we have seen in the video at the beginning of the presentation. You can see a rather peculiar trend of the velocity, which is basically made of a sequence of bells, which are very peculiar of biological motion. If you think about atomic gesture that you may perform, you start by accelerating, and then at some point in the middle of the gesture, you start accelerating to finally stop. The presence of these bells are, as I said, peculiar of biological motion, so you can see them even in more noisy situations. For example, while I am gesticulating, when I am talking, or again, considering a sequence of pointing actions. And instead, a rather different trend is in the case of a pendulum, of the trajectory that you use to describe the behavior of a pendulum. Okay, so once that you have the velocity and the acceleration, you can compute the curvature, and there you are done. You can compute also the angular velocity and the radius of curvature, and you are ready, let's say, to test the validity of the 2/3 power law even in our case. So we start by considering a set of sequences of biological actions, pointing, transporting, and so on. And we consider subsets of the trajectory in which the parameter alpha is 0, so to use the laws involving the curvature and the angular velocity, and try to evaluate let's say, the value of the exponent to see whether the 2/3 power law was valid. The dots refer to the exponent that we estimate for each subpart of these trajectories. And as you can see, all these dots are rather, even if there is noise, of course, but are very close to the reference, which is the 2/3, and which is the red dotted line. The situation instead is, let's say, less clear in the case of non-biological examples, and this seems to speak in favor of the validity at some level of the law, even in our noisy, for our noisy data. So at each time instant, we describe the region of interest in which the motion is occurring with a set of features, which are the one that we have discussed in the previous slides. And then we can concatenate such vectors over time to estimate in some sense, to compute in some sense a temporal description, considering different temporal windows size. And then we use machine learning to classify such data. Of course, we can model the problem as a binary classification problem in which we have two sets of examples. The first one are the examples of the biological actions. The other one are made of non-biological examples, and then you can try to separate the two sets of data, for example, by using the well-known support vector machines. But also you can reason on the fact that as I said, biological examples have, in some sense, rather peculiar characteristics. So you can try to discriminate the set of biological examples with respect to all the rest. So in this case, the problem is the problem of one-class classification. You can still use one-class SVMs, or instead using other examples, other methods, for example, the one I started there, in which the aim is to estimate the geometrical support of a set of data with the aim of distinguishing such set with respect to all the rest. In that case, it is based on, let's say, the study of the spectral properties of the grand matrix. Okay. So here there are some examples of output. Of course, we can design our method to work online. So at each time instant, on a video of test, we can associate with the test datum a set of SVM scores related to the fact that we might have more than one classifiers, each one trained on a different set of data or related to the same information but considering different windows size T. And so the region of interest are color-coded according to the system feedback. Yellow, that maybe it was at the beginning, means that some motion was observed, but there is not enough evidence to give a feedback for the system. Green refers to biological motion, red refers to non-biological motion. In the case of toy car, if you notice, there was the presence of both, so of my hand, so a biological example, and of a toy car. And in some sense, the system was confused by this, and this is mainly because our low-level analysis is very simple. When you, let's say, select the region of interest, we do not consider the fact that it might be composed by different connected components, possibly related to different sources of motion. So we average everything, and we lose this kind of information. So of course, this is a straightforward improvement possible for the system. Okay, so just a few words about this problem. Is it if I don't know?
Yes, sure.
Okay. It has been experimented by observing people performing lifting action, transporting action, or with let's say, manipulating some objects, and measuring the dynamic of the arm with respect to using markers, that the velocity of the action strictly depends on the weight of the object. The lower the weight, the higher the velocity of the action. So we tried to understand whether it was possible to infer the same, more subtle detail about property, about the motion, using the same information used before. This is a plot over time of the velocity magnitude for two different sequences of lifting actions involving two different objects of different weight. And as you can see, as a first let's say, temporal stage of assessment, there is a rather assessment of the peaks that are consistently higher in the case of object of lower size. And in fact, the average size of the peaks are different for the two cases. So we try to model the problem exactly in the same way as before, considering two sets of data. So this is a binary classification problem. In this case, the two sets of data are related to the two lifting actions related to the two different weights. And as you can see, over time, the SVM scores tend to be more correct when the, let's say, actual gesture is occurring. Okay, so from these preliminary experiments, we observed that some features related to peculiarity of the biological motion might be used maybe for designing more complex motion analysis system. Of course, there are many future directions for investigations. First of all, we might consider more complex descriptions, low-level descriptions from one point to a set of points within the region of interest. Then, of course, ICAP has a stereo vision, so why not considering the use of stereo information rather than a single stream or video as we have did so far. And of course, all this, let's say, reasoning about the optical flow may be transported using the same flow. And then, of course, the view invariance with respect to which we have not results, and also the specificity of the question might be increased. Try to classify very specific classes of actions rather than, let's say, groups more generic of biological with respect to non-biological examples. Okay, thank you.
Any questions for Nicolletta?
Do you take any biological view about the origin of the two-third power law? I mean, some people have related it to optimal control.
I'm sorry?
Do you take any particular view as to the origin of the two-third power law, biologically speaking?
The idea was, okay, I'm a computer vision person, so all the, let's say, questions related to biological inspired systems came from me, but also from my collaborators from IIT, which are more focused on this field. And yes, we started to learn things about it because we found, I don't know, let's say, the works we found were focused on, let's say, peculiarities of the biological motion. It's not so easy to find works about it, so we tried to take all the reasoning on that case. In that case, the experiments were performed on rather controlled settings, very specific actions, and so tried to test whether the same kind of characteristics might be observed also in our setting.
Thank you very much, Nicolletta. Okay. So now with the working screen.